So we're going to start chapter 6. It's called confidence intervals. In 6.1, we're going to construct confidence intervals for the mean, for an unknown population mean. We want to try to figure out what that is. In section 6.2, we also want to construct confidence intervals for the mean. It's just, in this case, our sigma will be unknown, or we'll have essentially small samples. And then in section 6.3, we're going to want to do the same thing, construct confidence intervals, but not for the population mean, but yet the population proportion. So it's kind of how they do on the news to tell you the presidential approval rating and things like this. We're not going to cover 6.4 in this course. So we'll start in section 6.1. Confidence intervals for the mean. I'll explain more as we go along what a confidence interval is, but I want to direct your attention back to chapter 5, section 4. It might be a good time to pause and go look at the end of the second video for section 5.4, where we did an example involving filling up milk containers to determine if a machine was properly set or not. The idea there was the machine said it was set for 64 fluid ounces. We found the sample of 40 containers had an average of 64.05, and that was enough information to actually tell us that the machine was probably broken. But the point I want you to take from that is, look, we only grabbed 40 containers and we found 64.05. That was enough to tell us that the machine wasn't properly set. So a sample of 40, the average from a sample of 40 is probably really close to the actual average itself. And that's what we want to do in chapter 6, essentially. From sample data, try to determine an unknown population value, like what is the average amount of turkey an American eats at Thanksgiving? Well, I don't know. You'd have to ask all Americans to weigh their turkey, and they're probably not going to do that. So what we can do is we can get a sample, say, ask 50 Americans, please weigh how much turkey you're going to have. And the average from those 50 is probably going to be a good estimate for the average of all Americans. That's exactly what chapter 6 is about. So in section 6.1, we have the following objectives. We want to find a point estimate and a margin of error for the population mean. So we're going to use an X bar to try to approximate mu. We want to construct actual confidence intervals. We'll explain those a little bit more in a moment. And then we're going to talk about determining a minimum sample size requirement when we wanted to estimate the actual population mean. So first of all, we're going to look at a point estimate. It's a single value estimate for a population parameter. If we want to estimate the population mean mu, the most unbiased point estimate would be X bar. If we want to know the population mean mu, we should use a sample mean X bar. Okay, so let's just look at an example here. 40 users of a social media site, let's just imagine Facebook, have been asked, how many friends do you have? And we can see all their responses down here. We have some with few friends, like, or I don't know, 82 or 65 or 58, 51, to those that have more friends than others here, 214. Okay, so these are 40 people, how many friends they had on Facebook. If we calculate the average, we just have to add them all up and divide by the 40, you get 130.8. So our point estimate for the mean number of friends all users have on, say, Facebook is 130.8. So we're trying to estimate how many friends, what is the average number of friends for all users of Facebook? And we're basing this 130.8 on only a sample of 40. So our point estimate for mu is 130.8 because it's the X bar we got from this sample. But 130.8 might not be exactly correct. And if we think of continuous variables, the probability that's exactly correct is 0. But maybe it's going to be close to 130.8. So can we create an interval, add some value and subtract the same amount of value to construct some sort of an interval where we might be able to have a certain amount of confidence in it? Say maybe we want to be 90% confident. Well, then we can construct an interval that will contain 90% of such X bars. Well, how do we do that? First, we just determine what level of confidence that we want. It will be the probability that the interval that we were just looking at is going to estimate, the interval is actually going to contain the population parameter, in our case, mu. So the idea here is based upon the central limit theorem. So remember, the central limit theorem tells us when x bars are going to be normally distributed. Part 1 says if our sample size is 30 or more, the x bars will be normally distributed enough to use the normal distribution. Part 2 said if the population itself was normally distributed, then so will the x bars, regardless of the sample size. So here's the gist. If we fix our level of confidence C, say to 90%, then we only really want the central 90%. So this area here in blue would be 90%. Now it will be relatively easy for us to determine what z-scores, a positive and negative z sub c, would separate the central 90% from not. We'll show you how to do this in the next slide. So this will give us 90%, and then maybe we can figure out how to convert these back into x bars some way to give us the limits, lower limit and upper limit for the interval we want to construct. So if the central area is C, then what's not blue under this curve has to be 1 minus C, or complementary. So you could take 1 minus C and cut each in half, because each tail is the same due to the symmetry of this picture. Then we can find the z-scores, so-called critical z-scores, z sub c, using the standard normal distribution table. So let's look at an example of 90% confidence. That means we want to be 90% confident the interval we construct will contain what we're looking for, will contain mu. So the central area is 90%, so 10% is not blue, and we'll cut it in half. Half of 10% being 5% will be down here, the other 5% up here. So now essentially we just look up a z-score. Find me a z-score that has an area to its left of 0.05. That'll give us the negative z sub c. That would be the easiest way to do this problem. If you're not comfortable with this, this was in our section 5.3, so please review that. You find these z-scores to be negative 1.645 here, and due to the symmetry of the standard normal over 0, the other z-score is just the positive version. So the critical scores for a 90% confidence interval for the standard normal distribution will always be z-scores of plus or minus 1.645. Now, sampling error is defined as the difference between the point estimate and the actual population parameter value. So our point estimate is our x bar that we get from our sample, and the actual population parameter is mu. So when we're dealing with mu, as we are in section 6.1 and 2, the sampling error is simply x bar minus mu. Technically, we should have absolute values around this because we want to think about the distance. How far away was our point estimate from the population parameter? But mu is generally unknown. That's the point of chapter 6. We don't know what mu is. We're trying to find it. So it's going to be impossible for us really to calculate the actual sampling error because we don't know mu. Also, x bar is going to vary. If I got a different sample of, say, for instance, that Facebook example we were looking at, if I looked at 40 other people, I probably won't get exactly 130.8 for my x bar. So x bar is going to vary from sample to sample. Mu is unknown. So the sampling error, we're not going to be able to actually calculate it. But what we're able to do with this sampling error, x bar minus mu, is we're going to put a maximum value on it. So if we fix our level of confidence C, then we're not going to care what happens outside of that central region of C on the standard normal distribution table. So we're going to actually be able to cap the sampling error if under a given confidence C. The formula here is denoted by E for margin of error, Z sub C times sigma sub x bar. From previous chapter, we know that sigma sub x bar is sigma over the square root of n. So the margin of error formula is actually pretty easy. It's Z sub C. This is completely determined by your confidence. Sigma, the population standard deviation, divided by the square root of the sample size. Now this note here in blue is quite important. If the sample size is bigger than or equal to 30, meaning in central limit theorem part 1 works, then we can actually use the standard deviation we get from the sample, S, in place of this sigma here. It's not very realistic to think we know what sigma is. Remember, sigma is the population standard deviation. What we're trying to do in this chapter is to determine what mu is. We don't even know what mu is. How would we know sigma, which is like the typical spread data is from mu? So what's much more realistic is to have a large sample size, and we won't be dependent on knowing sigma. We can simply put S in its place. And I wanted to show you where this, oh, by the way, this is called margin of error, sometimes called the maximum error of estimate, or known as the error tolerance, but we'll refer to it much more often as the margin of error. I do want to show you quickly where this formula comes from. So recall the formula that we use to standardize an X-bar. When we know X-bars are normally distributed, either central limit theorem part 1 or part 2 works, we know how to standardize an X-bar. We use this formula here, the right-hand side. We take the X-bar we want to standardize minus mu, the population mean, divided by sigma, then divided by the square root of n. Now, X bar minus mu is actually this, the sampling error we were referring to a couple slides ago. So let's just solve this formula, z equals this business for X bar minus mu. If you do that, you'll get X bar minus mu is z sigma over the square root of n. So z sigma over the square root of n is the formula for our sampling error. And on the right-hand side, sigma is just a constant. N is our sample size, another constant. So the only variable here is z. The bigger z is, the bigger the sampling error is. So if we fix a level of confidence C and say we only care to be 90% confident or maybe 95% confident or whatever the confidence is, then we don't care to actually go beyond the z sub c that gives us that confidence. So the margin of error is simply the largest we're going to allow this to become. The biggest this becomes is when z becomes z sub c. So the only difference between the right-hand side of this equation and this is that this is z sub c. So in pictorially, here's what's happening. If this is, say, 90% confident, we only care about the central 90% of X bars. So we don't care to become bigger than this z or smaller than this z. So the biggest that this sampling error will ever become under a given level of confidence is the right endpoint of this shaded region, z sub c. So that's where the margin of error formula comes from. Let's do an example. Let's go back to the social networking website data, the 40 data points, the Facebook ones we were talking about earlier, and 95% confidence level. And let's find the margin of error for the mean number of friends used for the website. And we're going to assume the sample standard deviation is about 53. But look, we got 40 data points. We could just go in and calculate the sample standard deviation S, and it's just about 53. So we have a 95% confidence interval, so we'll shade the central 95% of the standard normal distribution. There's 5% not included in the blue region. Cut 5% in half, and you get 2.5% here in the left tail, 2.5% in the right tail. Find those critical z-scores, and hopefully you're comfortable enough to find that they should be negative 1.96. That would be the easiest one to find. Just look up 0.0250 as an area in the table. The closest z-score that will give you that is a negative 1.96. The positive is always just the positive version of this negative one. Okay, so we know our critical score is z sub c of 1.96. Okay. Again, to note, you can approximate the distribution of sample means x bar with a normal curve because of the central limit theorem part 1, being that n was greater than or equal to 30. So we just then plug everything into this margin of error formula. Z sub c we found to be 1.96. Now we don't know sigma because we only looked at 40 Facebook users, but we did find their sample standard deviation S was 53. And since the sample size was 40, greater than or equal to 30, we can use S instead of sigma. So perform the calculation and you find the margin of error to be 16.4. Okay, Well, what does that mean? Well, it means we're 95% confident that the margin of error for the population mean is 16.4. We'll make this make more sense in the next slide. A confidence interval itself is simply take your point estimate x bar and add and subtract the margin of error, okay? And then the probability that the confidence interval actually contains mu, this unknown population mean, is going to be C, whatever confidence we use to construct the margin of error. Okay, just in steps, find a sample statistic n and x bar. So if we want to find the population mean mu, go and get yourself an x bar. The larger the n, the better, the more you're learning about the population. Calculate the sample mean from the sample. If we know sigma, great. It should be given to us. If we don't know sigma, then as long as we have a large sample size, as long as n is greater than or equal to 30, we can calculate its sample standard deviation using this formula from way back in chapter 2, and calculate its sample standard deviation and use that instead of sigma. Next up, find the critical value given the level of confidence. This comes from the standard normal table. If you look at your standard normal table, you'll also see a little table called critical values, and those are for very common confidence interval levels, 80%, 90, 95, and 99%. Now we go ahead and calculate our margin of error. We know Z sub C from the prior step. We either have been given sigma or we have a large sample where we've calculated S and used this in S in the place of sigma and divide by the square root of your sample size. Then simply add and subtract your margin of error from the point estimate and you're done. That's how a confidence interval goes. So let's go ahead and finish off the original problem. Construct a 95% confidence interval for the mean number of friends for all users of the website. So before we calculated the point estimate from the 40 to be 130.8 if we averaged all 40 from our sample, and prior we've calculated the margin of error to be 16.4. So we simply subtract and add the margin of error, giving us the lower point of our confidence interval and the upper point of our confidence interval. So what we can say is we're 95% confident that the actual average number of friends for all users of this website is between about 114 and 147. We could graph it just to see a graphical representation. And we're 95% confident that the actual mean mu is somewhere in this region between 114 up to 147. Another example, a college admissions director wants to estimate the mean age of all students currently enrolled. Let's just imagine it's a really, really big school, so it would be hard for us to calculate the average age of all of them. So they randomly sampled 20 students and found the mean age to be 22.9 years old. From past studies, the standard deviation is known to be 1.5 years. They're telling us sigma. And the population is normally distributed. They want us to construct a 90% confidence interval. So a couple of things grab my attention. First of all, this sample is 20. This is definitely not greater than or equal to 30. So when that happens, you should pause for a moment and say, well, wait, that certainly doesn't satisfy central limit theorem part 1. Central limit theorem part 2 requires us to know the population is normally distributed. Well, they tell us that the population is normally distributed here. Okay, so great, central limit theorem part 2 works. The last thing we have to say is, do we know what sigma is? Because since we have a small sample, S from a small sample is not always a very good approximation for sigma. The sample standard deviation from small samples is not always a good approximation for the standard deviation of the entire population. But they told us right here from past studies, the standard deviation is known to be 1.5. So we know sigma, we know the population is normally distributed. Central limit theorem part 2 will allow us to continue. So we'll construct a 90% confidence. 90% confidence interval, draw the curve, shade the central 90%. There we go. 10% is not in the center, so half of 10% or 5% is in each of these two tails. We could find the cutoff z-scores that will give us the negative z sub c, 5% to its left, and the positive z sub c, 5% to its right. You should find those to be plus and minus 1.645. We plug that into our margin of error formula, 1.645. We were told sigma was 1.5. Divided by the square root of our sample size is 20, and we find to be 0.6. Add and subtract that from our point estimate. Found that the average of our 20 had mean age of 22.9. So subtract the margin of error, add the margin of error, and we've just developed the confidence interval. We are 90% confident that the average age of all of the students on this college campus is between 22.3 and 23.5. Okay. I want to caution you. What we've just done here is found an estimate for the average of all the college students. This says nothing about individual college students. It doesn't say that 90% of the college students are between 22.3 years and 23.5 years old. It doesn't say that at all. What it says is if we averaged all of the college students, that we're 90% confident the average of all of them are between these two values. So this says nothing about individual. Again, just pictorially, with 90% confidence, we can say the mean age of all the students, mu, is somewhere between 22.3 and 23.5 years old. Okay, you should definitely try a couple of these problems, make sure they make some sense. But there's one more thing we want to cover here is, well, first of all, let's talk about the interpretation. Don't worry too much about this slide, but we should try to speak precisely. So remember, mu is a fixed number. It's either in the confidence interval or it's not in the confidence interval. The incorrect interpretation is that there's a 90% probability the actual mean is in that interval we just constructed. The correct interpretation is that if we repeatedly did this, repeatedly asked 20 people how old they were and calculated the 90% confidence interval based upon their X bars, that 90% of those confidence intervals are going to contain the mu we're looking for. Pictorially, it's easier to see. If I did this 10 times, so here's a confidence interval for a sample of 20 students, and then we do it again, 20 other students, and we get all these. There are 10 of them. A 90% confidence interval says that 90% of these should contain the actual mean mu. And notice the mean mu here is represented by the pink line. And this 1, 2, 3, 4, 5, 6, 7, 8, 9 of them do contain it. This confidence interval came out too low to contain it. So 9 out of the 10 did, therefore there's our 90%. That's really the proper way of interpreting the results. But this is a reasonable kind of, although it's incorrect, it's still all right to think our confidence interval has 90% probability of containing what we're looking for. Okay, one last topic we cover in section 6.1 is a minimum sample size requirement. So given a level of confidence C and the level of margin of error E, we want to know what minimum sample size is needed to construct the estimate that would satisfy the confidence and the desired margin of error. This formula is not new. It's actually the margin of error formula solved for n. It's just a little algebra. So it's not a new equation. It's the same equation as the margin of error. So if we don't know what sigma is, as this requires us to, we can estimate it using a sample standard deviation S, just provided the sample is at least size 30. So 30 is our magic number between small samples and large samples. So we'll refer to samples of size at least 30 as large samples and samples less than size 30 as small samples. So let's give an example. We want to estimate the mean number of friends for all users of some website. How many users should be included in the sample if we want to be 95% confident that the sample mean we get from the sample is within 7 friends of the population mean? We're going to assume the sample standard deviation is about 53. Well, you know, we calculated this 53 before from a sample of size 40, so it's a good estimate for sigma. So just to recap, look, we want to know the average amount of friends. that some website, or the average amount of users, the average amount of friends for, let's just say, the average user on Facebook. We want to be 95% confident that the average we get from our sample is within 7 friends of the actual average. So this 7 is our desired margin of error E, and our confidence is 95%. We have a good estimate for sigma from a large sample's standard deviation S. So we can just apply this formula. Again, we need the critical values for a 95% confidence interval. Those come out to be plus and minus 1.96. And then we can simply apply the known values. 1.96 for our confidence. Sigma can be approximated by a large sample S, which ours was 53, and our margin of error is desired to be 7. We plug this into the minimum sample size requirement, and careful with the calculation, we come up with 220.23. So what this is saying is go and sample 220.23 people, and the X bar you get from them, we will be 95% confident that it's within 7 friends of the actual average mu. But we can't talk to 20.23 people. Okay, so we're always going to have to round this up. I know most of you might be thinking, well, that rounds to 220. But this 0.23 of a data point actually gives us mathematically information. So we have to round up so we don't lose information. So if we get at least 221 users in the sample, we will be 95% confident that the X bar from them will be within 7 friends of the actual value of mu. Okay, it's called the minimum sample size requirement. All right, that's section 6.1. So make sure you understand finding a point estimate. Point estimate isn't really a great way to estimate something. We definitely need to add and subtract this margin of error so we can have some confidence or some probability that what we did contains what we're looking for. That's why we constructed and interpreted confidence intervals, and then finally determined a minimum sample size required for a given confidence and margin of error when wanting to determine mu. Well, I hope that all makes sense, guys. As always, feel free to email me with any problems or questions after you review these videos, the PowerPoints, and try some problems yourself. I hope everybody's doing well. Take care. I'll see you in the next video.